There is nothing you need to do right now, nothing to think about, nothing to figure out. Just settle in and let these quiet facts about our galaxy drift past you, soft and slow like light traveling across an enormous, patient sky. The Milky Way contains somewhere between 100 billion and 400 billion stars. That number is so large it has no real feeling to it, and that is perfectly fine. You do not need to hold it. Just let it rest there, somewhere at the edge of your awareness, the way a distant sound rests at the edge of sleep. Welcome, this is a slow and gentle journey through some of the quieter facts about the galaxy we live in. There is no rush here and there is nowhere to arrive. The Milky Way has existed for around 13 billion years and it is in no hurry. Neither are we. These facts are small and calm. Some of them are about size, some are about light, some are about the way things move through space slowly and steadily over timescales too long to feel urgent. You are allowed to let your eyes grow heavy. You are allowed to drift. The facts will continue quietly whether you are fully awake or already somewhere softer. Everything here is safe. Everything here is slow. The galaxy is very old and very wide, and none of what happens inside it is in any particular rush. The Milky Way is a barred spiral galaxy. It has a large central bar of stars running through its middle and spiral arms that curve outward from the ends of that bar. Our solar system sits in one of those arms, about halfway between the center and the outer edge. We are not at the center of anything, and that is a calm and ordinary place to be. The name Milky Way comes from how the galaxy looks from Earth on a dark, clear night. It appears as a soft, hazy band of white light stretching across the sky. Ancient observers described it as a river of milk, and many cultures gave it names that meant something similar: quiet, pale, stretched across the darkness. The galaxy is roughly 100,000 light-years across. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. Even at that speed, crossing the full width of the Milky Way would take 100,000 years. Light does not stop to rest. It moves constantly at the fastest speed anything in the universe is allowed to travel, and it would still take that long. The galaxy is simply that wide. Our solar system orbits the center of the Milky Way. It takes approximately 225 to 250 million years to complete one full orbit. This is sometimes called a cosmic year or a galactic year. Since the Earth formed, it has completed roughly 18 to 20 of these orbits. The dinosaurs lived during a different galactic year than the one we are in now. The center of the Milky Way is a busy and dense region. There are many more stars packed together near the core than there are out here in our quieter arm of the galaxy. The night sky, if you lived near the galactic center, would be filled with stars so numerous and close together that it would never fully darken. But we live in a calmer neighborhood where the stars have more space between them and the sky can grow properly dark. At the very center of the Milky Way there is a supermassive black hole. It is called Sagittarius A star. Its mass is approximately 4 million times the mass of our Sun. That is a very large amount of matter compressed into a very small region of space. The black hole does not do anything dramatic from our distance. It sits quietly at the heart of the galaxy, pulling everything into a slow, wide orbit around it. The Milky Way has a halo, which is an invisible spherical region surrounding the visible disk of the galaxy. This halo is made mostly of dark matter, which is a substance that does not emit or reflect light but does exert gravitational pull. Scientists know it is there because of the way it affects the movement of stars and gas, but it cannot be seen directly. A large, quiet shell of invisible matter, wrapping around everything we can observe. The disk of the Milky Way is relatively thin compared to its width. It is about 1,000 light-years thick in most places, though it thickens toward the center. Imagine a very wide, very flat shape like a disk pressed nearly flat with a rounded bulge in the middle where the bar and core are located. There are between 100 billion and 400 billion individual stars in the Milky Way, as mentioned at the start. Astronomers are not certain of the exact number because so much of the galaxy is hidden from our view, blocked by dust and gas and the sheer density of stars in the central regions. The estimate is wide, and that is fine. Precision is not always available in a galaxy this large. Most of the stars in the Milky Way are smaller and dimmer than our Sun. The most common type of star is called a red dwarf. Red dwarfs are cool, faint, and very long-lived. Some of them will burn steadily for trillions of years, long after stars like our Sun have faded. They are quiet, patient stars, and they make up the majority of the stellar population of our galaxy. Our Sun is a fairly average star in terms of size and brightness. It sits comfortably in the middle range of stellar classification. It is not particularly hot or particularly cool, not especially large or especially small. It is a calm, yellow-white star of a type called G-type, and it has been burning steadily for about 4.5 billion years. It is expected to continue for another 5 billion years or so before it begins to change. The Milky Way has several major spiral arms. They are named after the constellations in the directions where they are most visible from Earth. There is the Perseus arm, the Sagittarius arm, the Centaurus arm, and others. Our solar system sits in a smaller partial arm called the Orion arm, sometimes called the Orion spur. It branches off between two of the larger arms and is quieter and less densely packed than the main spirals. Stars in the Milky Way do not all orbit the galactic center at the same speed. Stars closer to the center tend to orbit faster, and stars farther out orbit more slowly, though the relationship is not perfectly smooth. The variation in orbital speeds across the galaxy was one of the early clues that led scientists to suspect the existence of dark matter. The outer stars were moving faster than they should have been, given the visible mass of the galaxy. Something invisible was adding extra gravitational pull. That something is what we now call dark matter. The Milky Way is not perfectly flat. Its disk has a slight warp toward the outer edges, bending gently upward on one side and downward on the other. This warp is thought to be caused by the gravitational influence of nearby satellite galaxies pulling on the outer regions of our galaxy over long periods of time. A slow, gentle bend spread across tens of thousands of light years. The Milky Way has satellite galaxies. These are smaller galaxies that orbit our own, held in place by gravity. The two most well-known are the Large Magellanic Cloud and the Small Magellanic Cloud. They are visible from the southern hemisphere as faint, cloud-like patches of light in the night sky. The Large Magellanic Cloud is about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years away. Both are irregular in shape, meaning they do not have a clean spiral or elliptical form. There are other smaller satellite galaxies orbiting the Milky Way as well. Some of them are so faint and diffuse that they were only discovered in recent decades, when telescopes became sensitive enough to detect them. The Sagittarius dwarf galaxy is one example. It is currently being pulled apart by the gravitational force of the Milky Way, its stars slowly being absorbed into our galaxy over millions of years. The process is gradual and without drama. One galaxy quietly merging into another over an almost incomprehensible span of time. The Milky Way itself is on a slow path toward a large neighboring galaxy called Andromeda. The two galaxies are approaching each other at roughly 110 kilometers per second. In approximately 4.5 billion years, they are expected to begin merging. This will be a very long and gradual process. Galaxies are mostly empty space, so the merger will not be a collision in the way we might imagine. Stars will not crash into each other. Instead, the two galaxies will pass through each other, their gravitational forces reshaping both structures over hundreds of millions of years, until eventually they settle into a single, larger galaxy. Astronomers have a name for the galaxy that will result from this merger. They sometimes call it Milkomeda, a combination of Milky Way and Andromeda. It will likely be an elliptical galaxy, rounder and less structured than either of the two spirals that formed it. Our sun may still exist at that point, though it will be very old and beginning its transition into a red giant. Whether Earth will still be habitable is uncertain, but the quiet merging of galaxies will proceed regardless. The stars of the Milky Way are not all the same age. The oldest stars in the galaxy formed very early, when the universe itself was young, more than 13 billion years ago. These ancient stars are found primarily in the galactic halo and in dense clusters called globular clusters. They are made almost entirely of hydrogen and helium, the two elements that existed in abundance after the early universe cooled. Heavier elements had not yet been formed in significant quantities. Heavier elements are created inside stars. Through the process of nuclear fusion, stars combine lighter elements into heavier ones over the course of their lives. When massive stars reach the end of their lives and explode in events called supernovae, they scatter those heavier elements out into the surrounding space. That material is then available to be incorporated into new stars and planets that form later. Our solar system contains heavy elements like iron, carbon, oxygen, and silicon because earlier generations of stars lived and died before our sun was born. Everything on Earth, including every human body, is made of material that was forged inside ancient stars. The Milky Way continues to form new stars. In the densest regions of gas and dust, gravity causes material to slowly collapse inward, growing denser and hotter until nuclear fusion begins at the core. A new star is born. This process takes millions of years and happens throughout the galaxy at a slow but steady pace. It is estimated that the Milky Way forms somewhere between 1 and 3 new stars each year on average. Star-forming regions are often located in the spiral arms of the galaxy, where gas and dust are more concentrated. Some of these regions are visible as glowing clouds called nebulae. The Orion Nebula, which is visible to the naked eye as a faint smudge below the belt of Orion, is one such region. It is a stellar nursery, where hundreds of young stars are currently in the process of forming, surrounded by the remaining gas and dust from which they emerged. The space between stars in the Milky Way is not completely empty. It is filled with what astronomers call the interstellar medium. This is a very thin mixture of gas and dust spread across the vast distances between stellar systems. In some regions it is denser, forming clouds. In others it is so thin that it is closer to a vacuum than anything we can create in a laboratory on Earth. But it is never entirely nothing. There is always something drifting through the spaces between stars, even if that something is only a few atoms per cubic centimeter. The interstellar medium is made up mostly of hydrogen. Some of it is in the form of individual atoms, some in the form of molecules, and some is ionized, meaning the hydrogen atoms have lost their electrons due to the energy of nearby stars. The dust particles in the interstellar medium are tiny, much smaller than the particles in household dust. They are made of carbon, silicates, and other materials, and they play an important role in the formation of stars and planets by providing surfaces on which molecules can form and clump together. Light from distant stars and objects is affected by this interstellar dust as it travels toward us. The dust scatters shorter wavelengths of light, particularly blue light, more than it scatters longer wavelengths like red. This means that objects viewed through dense regions of interstellar dust appear redder than they actually are. Astronomers account for this effect when studying distant objects, adjusting their observations to correct for what is called interstellar reddening. The Milky Way rotates, not like a solid disk spinning all at once but differentially with different parts moving at different rates. The inner regions complete their orbits faster than the outer regions, though as mentioned earlier, the relationship is not perfectly simple due to the influence of dark matter. This differential rotation means that the spiral arms are not fixed, permanent structures. They are more like density waves moving through the galaxy, regions where stars and gas pile up temporarily before moving on, the way a slow spot in traffic causes cars to bunch together even as the individual cars keep moving. Globular clusters are some of the oldest and most beautiful structures associated with the Milky Way. They are dense, spherical collections of stars, sometimes containing hundreds of thousands of stars packed into a relatively small region of space. There are about 150 known globular clusters orbiting the Milky Way, forming a spherical halo around the galaxy's disk. The stars in globular clusters are among the oldest in the universe, and studying them gives astronomers a way to measure the age of the galaxy and the universe itself. Open clusters are different from globular clusters. They are looser groupings of stars, typically younger, and found within the disk of the galaxy rather than in the halo. The Pleiades, sometimes called the Seven Sisters, is a well-known open cluster visible in the night sky. Open clusters tend to disperse over time as the stars gradually drift apart under the influence of gravitational interactions and the general motion of the galaxy. The Milky Way emits radiation across the entire electromagnetic spectrum, not just visible light. Radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays are all produced by different objects and processes within the galaxy. Much of the galaxy is invisible to our eyes but can be detected by specialized telescopes tuned to different wavelengths. When astronomers look at the Milky Way in radio waves, an entirely different picture emerges, revealing structures and features that are completely invisible in optical light. Pulsars are one of the more unusual objects found within our galaxy. They are the rapidly rotating remnants of massive stars that have exploded as supernovae. As they spin, they emit beams of electromagnetic radiation that sweep around like the beam of a lighthouse. When that beam happens to point toward Earth, we detect regular pulses of radio waves or other radiation. Some pulsars spin hundreds of times per second. They are extraordinarily dense objects, packing the mass of one or two suns into a sphere only about 20 kilometers across. Neutron stars, of which pulsars are one type, are among the densest objects in the universe. A teaspoon of neutron star material would have a mass of roughly 10 million tons on Earth. They are the collapsed cores left behind after certain types of stellar explosions. If the collapsing core is massive enough, gravity overwhelms even the resistance of neutron matter, and the object collapses further into a black hole. If it is just below that threshold, it becomes a neutron star, stable and extraordinarily compact, spinning quietly in the remnants of the explosion that created it. The Milky Way contains an unknown number of black holes, supermassive ones like Sagittarius A star at the center and stellar mass black holes, which are the remnants of individual massive stars. Stellar mass black holes are much smaller, typically between 5 and several tens of times the mass of the Sun. Astronomers estimate there could be millions or even hundreds of millions of stellar mass black holes scattered throughout the Milky Way, most of them invisible and detectable only if they interact with nearby gas or a companion star. When a black hole pulls material from a companion star, that material forms a flattened, spinning structure around the black hole called an accretion disk. As the material spirals inward, it heats up dramatically and emits X-rays. These systems are called X-ray binaries, and they are one of the primary ways astronomers detect stellar mass black holes. The process is steady and continuous, the material falling slowly inward over long periods of time, glowing in wavelengths invisible to the human eye. The temperature of the gas in different parts of the Milky Way varies enormously. Dense molecular clouds, where new stars are forming, can be extremely cold, just a few degrees above absolute zero. The gas surrounding hot young stars can be heated to tens of thousands of degrees, and some of the diffuse gas in the halo of the galaxy can reach temperatures of millions of degrees, though it is so thin that it contains very little actual thermal energy. Temperature and heat are not the same thing, and the near vacuum of hot halo gas contains far less energy than even a warm room on Earth. The Milky Way is part of a larger structure called the local group. This is a collection of galaxies bound together by gravity, spread across a region of space roughly 10 million light-years across. The local group contains more than 50 galaxies, though most of them are small dwarf galaxies. The two largest members are the Milky Way and the Andromeda Galaxy. The third largest is the Triangulum Galaxy, a smaller spiral located about 3 million light-years away. All of these galaxies move slowly through space together, held in a loose gravitational embrace. The local group itself is part of an even larger structure called the Virgo supercluster. This is a collection of galaxy groups and clusters spanning roughly 110 million light-years. At the center of the Virgo supercluster is the Virgo cluster, a dense collection of over 1,000 galaxies. The Milky Way sits near the outer edge of this supercluster, far from the dense central region, in a quieter and less crowded part of the larger structure. More recently, astronomers have mapped an even larger structure that includes the Virgo supercluster as one small part. This structure is called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans approximately 500 million light-years and contains the mass of roughly 100 million billion suns. The Milky Way is a tiny part of this vast web of galaxies, sitting in a quiet region far from the dense core of Laniakea, which is called the Great Attractor. The Great Attractor is a region of unusually high mass density that is slowly pulling everything in the surrounding region toward it, including our galaxy, across timescales of billions of years. The position of our solar system within the Milky Way has changed over time. As the Sun orbits the galactic center, it passes through different regions of the galaxy, sometimes moving through denser areas and sometimes through quieter ones. Some researchers have proposed that these changes in environment may have had subtle effects on Earth over geological timescales, though the evidence for this is not conclusive. What is certain is that the Sun continues its slow orbit, completing one full circuit every 225 to 250 million years, drifting through the galaxy at about 220 kilometers per second relative to the galactic center. The Milky Way has likely consumed smaller galaxies throughout its history. This process of galactic cannibalism is common in the universe. When a smaller galaxy drifts too close to a larger one, the gravitational tidal forces of the larger galaxy begin to pull the smaller one apart. The stars of the smaller galaxy are gradually absorbed into the larger one, often leaving behind streams of stars called tidal streams. Several such streams have been identified in the Milky Way, tracing the paths of ancient dwarf galaxies that were absorbed long ago. The Sagittarius stream is one example. It is a long arc of stars spread across a large portion of the sky, the remnant of the Sagittarius dwarf galaxy being slowly absorbed into the Milky Way. The stream has been mapped in considerable detail and wraps around the galaxy multiple times, tracing the orbit of the dwarf galaxy as it was torn apart over billions of years. The individual stars in the stream continue to move along that ancient path, even though the galaxy that once contained them no longer exists as a coherent structure. The distribution of stars in the Milky Way is not uniform. There are regions of higher and lower stellar density. The central bulge is the densest region, followed by the spiral arms. Between the arms, stars are more spread out and the space is quieter. Our own neighborhood in the Orion Spur is a relatively calm region, neither packed tightly like the galactic core nor as sparse as the outermost edges of the disk. It is a middle place, unremarkable in the best possible sense. There are regions in the Milky Way where star formation has essentially stopped. These are areas where the gas and dust have been used up or dispersed, leaving little material for new stars to form from. Over the very long term, star formation across the entire galaxy is gradually slowing. The universe is aging, and galaxies are slowly running out of the raw material needed to make new stars. This is a process unfolding over billions of years, too slow to detect on any human timescale but steady and inevitable. The chemical composition of the Milky Way has changed over time. The earliest stars were made almost entirely of hydrogen and helium. As generations of stars lived and died, they enriched the interstellar medium with heavier elements. Later generations of stars, including our Sun, formed from this enriched material and contain a wider variety of elements. Stars that formed more recently tend to have higher abundances of heavy elements than the oldest stars. Astronomers use the term metallicity to describe this abundance of elements heavier than hydrogen and helium, even though many of those elements are not metals in the everyday sense of the word. The Milky Way produces a magnetic field. This galactic magnetic field is very weak compared to the magnetic fields of planets or stars, but it spans enormous distances and plays a role in shaping the behavior of the interstellar medium. It influences the movement of charged particles through space, affects the formation of structures within gas clouds, and may play a role in the dynamics of spiral arms. The field is generated by the movement of charged particles throughout the galaxy and is maintained by processes that are still not fully understood. Cosmic rays are high-energy particles, mostly protons, that travel through the Milky Way at nearly the speed of light. They originate from various sources including supernova explosions and possibly the regions around black holes. When cosmic rays reach Earth, they interact with the atmosphere, producing showers of secondary particles that can be detected by instruments on the ground. The Earth's magnetic field and atmosphere provide protection from most cosmic rays, but high-energy ones occasionally reach the surface. They have been striking Earth continuously throughout its history, a constant quiet rain of particles from across the galaxy. The Milky Way has a feature called the galactic bar. This is an elongated, roughly rectangular structure made of stars that runs through the center of the galaxy. It is estimated to be about 27,000 light-years long. The spiral arms of the galaxy extend outward from the ends of this bar rather than from the center directly. Barred spiral galaxies are actually quite common in the universe. Roughly 2/3 of all spiral galaxies, including our own, have this central bar structure. The bar rotates slowly as a unit, at a different rate than the surrounding disk. The region at the very center of the Milky Way, closest to the supermassive black hole, contains a dense cluster of stars known as the nuclear star cluster. This is one of the densest stellar environments known to exist anywhere in the universe. Stars in this cluster are packed so closely together that encounters between them are far more frequent than in the quieter regions of the galaxy where our solar system resides. Despite being so close to a supermassive black hole, most of these stars orbit stably, following paths that have remained consistent over long periods of time. There are also extremely massive and luminous stars near the galactic center. Some of them are among the most massive stars known to exist anywhere, with masses tens or even hundreds of times that of our Sun. These stars burn very brightly and very hot, but their lives are correspondingly short. While our Sun will live for about 10 billion years in total, the most massive stars exhaust their fuel in only a few million years before ending their lives in spectacular supernova explosions. Near the galactic center, the rate of such explosions is higher than in quieter regions of the galaxy. The Milky Way has regions called superbubbles. These are large cavities in the interstellar medium, carved out by the combined energy of multiple supernova explosions and the powerful stellar winds of massive stars. When many massive stars form together and then explode in sequence over millions of years, their collective energy pushes the surrounding gas outward, creating an expanding shell around a relatively empty interior. These superbubbles can be hundreds of light-years across. Our own solar system may reside inside or near the edge of one such structure, sometimes called the local bubble, a region of relatively low-density interstellar gas surrounding our immediate neighborhood in the galaxy. The local bubble extends roughly 300 light-years in most directions around the Sun. Its interior is filled with very hot, very thin gas, the remnant of ancient supernova explosions that occurred in this region millions of years ago. The boundary of the local bubble is a denser shell of gas, and dust where star formation is currently taking place. Several young star-forming regions sit along this boundary, including some that are among the closest stellar nurseries to our solar system. Astronomers study the Milky Way using many different instruments and techniques. Radio telescopes detect the emission of hydrogen gas across the galaxy, allowing astronomers to map its distribution even in regions hidden from optical view. Infrared telescopes can see through the dust clouds that block visible light, revealing the stars and structures embedded within. X-ray telescopes detect the hot gas and compact objects scattered throughout the galaxy. Each wavelength of observation reveals a different layer of structure, and combining them gives a more complete picture of what the Milky Way actually looks like. One of the challenges of studying the Milky Way is that we are inside it. Unlike external galaxies which can be viewed from a distance and photographed as a whole, the Milky Way surrounds us in every direction. Mapping its overall structure requires piecing together observations from many different directions and distances, like trying to draw a map of a city while standing somewhere in the middle of it. Astronomers have made enormous progress in this effort, particularly with missions like the European Space Agency's Gaia spacecraft, which has measured the precise positions and motions of more than 1 billion stars in the Milky Way with extraordinary accuracy. The Gaia mission has transformed our understanding of the galaxy's structure and history. By tracking the movements of so many individual stars, astronomers can trace their orbits backward in time, reconstructing the history of the galaxy and identifying groups of stars that formed together or were captured from other galaxies long ago. The data from Gaia has revealed previously unknown streams of stars, refined measurements of the galaxy's size and mass, and uncovered evidence of ancient merger events that shaped the Milky Way into what it is today. The mass of the Milky Way is difficult to measure precisely. Estimates typically range from about 500 billion to 2 trillion times the mass of our Sun. Most of that mass is not in the stars themselves but in dark matter, which makes up the majority of the galaxy's total mass. The visible matter, including all the stars, gas, and dust, accounts for only a fraction of the total. This invisible component, detectable only through its gravitational influence, shapes the structure and dynamics of everything we can see. The age of the Milky Way as a whole is estimated at around 13.6 billion years, making it nearly as old as the universe itself, which is approximately 13.8 billion years old. The galaxy formed relatively soon after the Big Bang, as regions of slightly higher density in the early universe began to collapse under gravity, forming the first stars and eventually the larger structures we observe today. The oldest stars in the Milky Way carry a record of those earliest times, their chemical composition reflecting the simple, hydrogen-rich environment of the early universe. The spiral structure of the Milky Way is maintained by density waves moving through the disk of the galaxy. These waves are analogous in some ways to sound waves moving through air, regions of compression and rarefaction that travel through the stellar disk. As gas and dust encounter these density waves, they are compressed, triggering the collapse of clouds and the formation of new stars. The bright young stars that form in these regions illuminate the spiral arms, making them visible. The arms are not made of the same stars at all times, but are more like patterns that the material of the galaxy moves through. The night sky as seen from Earth gives only a partial and somewhat misleading impression of the Milky Way. From our position inside the disk, we see the galaxy edge on in the direction of the galactic plane, which appears as the familiar band of light crossing the sky on dark, clear nights. But in the directions perpendicular to the disk, above and below us in galactic terms, we're looking out through a much thinner layer of stars and into the intergalactic space beyond. The galaxy looks very different depending on which direction one looks, and our view of it is always that of an insider, embedded within the structure we are trying to observe.